Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us. It underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. These are the famous words of Carl Sagan, and they illustrate the fact that we are alone in the universe and that we must help each other in order to survive. As we push onwards to the edge of science and technology, we tend to forget about problems that no longer apply to us. Each and every day, there are new treatments for everything from the common cold to cancer. In the past century, we have found cures to countless diseases and infections, but one of the biggest issues facing us today is not a disease. It's not an infection. It's nothing. Having nothing to eat kills every day. On average, 10 people have died from hunger since I began talking, and another 150 will die before the end of this presentation.
Hunger kills more people each year than AIDS, malaria, and tuberculosis combined. In a world where we have AIDS treatment, malaria vaccines, and tuberculosis medication, why can't we ensure the nutrition of our people? In 2014, 795 million people, that's 1 out of every 9 people, suffered from chronic hunger. According to the United Nations, 21,000 of these people die every day due to hunger-related causes. More than 50% of these deaths are children. Due to poor maternal health, newborn infants in hunger-stricken areas are often born underweight and undernourished, prone to many sicknesses. Undernutrition in children under 2 years of age causes the irreversible stunting of growth. As these children grow up without the proper nutrition, they enter the vicious cycle of hunger. Children who are undernourished have a more difficult time in school, as the lack of food limits their attention span. As adults, they are plagued by chronic illnesses due to the undernutrition they experienced earlier in life. Their lack of health and education severely restricts their work opportunities, eventually leading to the formation of a family with no way to access the necessities of life. If this family has children, those children are born undernourished, and the cycle continues.
There have been many proposed solutions to solve world hunger. However, each of them comes with their own set of issues. Here are a few of the best ideas and their shortcomings. One idea is food donation. Enough food is cultivated each year to feed every person on Earth. Thus, the only issue stems from location and transportation of food. While the majority of the world's population could make some sort of food donation to help those struggling with hunger, it would only be a temporary solution. The process of shipping food is costly and unsustainable. It may save lives in the short run, but these efforts will simply cause the community to become dependent on handouts. Once these donations decrease in size, it is only a matter of time before the people run out of food and starve again. Access to credit has been another proposed solution to solving world hunger. Letting poverty-stricken farmers borrow money operates on the principle that they will be able to grow crops and then return the loan later. However, even the best of farmers may not be able to grow viable crops in their environment. As such, there is a high risk of failure when it comes to this approach. The ideal scenario would be to have a crop that can grow anywhere and is edible. Without these two key traits, providing access to credit may not be applicable on a global scale. Social change and empowering women has been another proposed solution to solving world hunger. The fundamental idea behind this solution is that increasing the power of women will give them access to food and capital, allowing to become providers for their families. Thus, this will be a higher food income for families. While this works well for developed countries, it has little to no impact in areas with no access to food. There are two main issues or types of hunger: lack of food and lack of access to food. Lack of food is what most people associate with hunger, and is typically depicted as barren wastelands with scattered groups of starving people. Lack of access to food is the hunger that is an issue in more developed areas like the United States, where there is food, but people lack the resources to buy the food. The lack of access to food is more of a logistical problem. Our group looked more at scientific, sustainable solutions to help where there is no food.
In his landmark book, On the Origin of Species, Darwin described the struggle for existence. This was the notion that because we on Earth have finite resources, every individual must compete in order to survive.
Yet the beauty of nature is that areas that are poor in natural resources, tundras, deserts, wastelands, are miraculously not devoid of life.
You are well familiar with what these life forms might be. These are sturdy, tenacious fighters that manage to tough it out under the harshest circumstances.
When you observe them peeking out from cracks in the concrete or blooming out of arid soil, appreciate that these are the exemplars of the struggle for existence.
When all other life has fled the land, they will remain. And in times of famine and drought where our common crops have failed us, can we really afford to be selective?
Perhaps it's time we expanded our definition of edible.
Our human bodies lack the requisite enzymes needed to break down cellulose, the main structural component of grasses. Our bovine companions, however, can. They use diverse microflora in their four stomachs to break down cellulose in a stepwise fashion. In principle, one could isolate these bacteria and amplify their expression of the enzyme and make use of that, but doing so is not a sustainable solution to world hunger. Culturing and isolating enzyme from microbes is frustrating work, as the discoverers of penicillin will tell you. But what if we were able to engineer grasses with the instructions for these enzymes built into them already? Here's how it would work. Using available genetic engineering protocols, we propose inserting various cellulase enzymes into the seeds of the arid grass Stepigrossis obtusa, a species found widespread across North Africa, Chad, Ethiopia, Southern Africa, Western Asia, and the Arabian Peninsula.
To prepare. Grass expressing the cellulase enzyme can be mixed with wild-type grasses. Using a mortar and pestle, grind the grass up to maximize surface area exposure. Drop the pH of the mulch with a controlled volume of vinegar or lemon to activate, and repeatedly grind to a paste. This paste is a glucose and fiber-rich substance that can be used as food filler in times of stress.
But won't the cellulase kill the grass?
Cellulase is actually a family of enzymes that work together to break down cellulose. We will engineer 10 variants of the same grass, each of which cannot function on its own. These 10 variants will be sold together as a seed starter pack. Furthermore, the pH of the soil that the grass would grow in is approximately 6.5, whereas the pH needed to activate the enzyme is approximately 4.2 to 5.4, which means that the enzyme will not be activated to degrade cellulose unless there is a drop in pH. This is where the lemon and vinegar comes in.
Will the grass be less fit for survival because they have to produce extra enzymes?
In order to control expression, we will use the BRZ1 promoter. This is a sequence that binds BRZ1 transcription factors, which are plant hormones that activate after plant germination and before flowering. That way, the relevant genes will only be expressed as the grass has the resources to grow.
Could this grass impact the local ecosystem? The ultimate goal of this project is to have grass which can grow and proliferate without the need of constant care and maintenance. Our genetically modified grass is edible and provides nutrients, but as this idea expands globally, we don't want it to destroy valuable ecosystems by competing with the indigenous plants and crops. This species is less fit for survival than the other species when it comes to reproducing, as some of the plant's resources must go into producing enzymes used in its own digestion. Because it does not possess any genes that would increase its fitness compared to other organisms, it should not negatively impact the survival of other local plants. Our implementation has been broken into year-long steps, and we have used published data to estimate the costs of each step. Our numbers were on the more conservative side, ensuring that the amounts would cover any required expenses, as well as additional research, assuming that we encountered some issues along the way. The first step of our plan is the research and development of the modified grass. This involves the insertion of 10 different genes into the genome. As mentioned earlier, each strand will get one of the 10 enzymes required in order to effectively break down cellulose. The cost for this section can vary depending on laboratory equipment access and whether it's being done at an academic institution versus a commercial one. Once the 10 strands have been made, it's important to test them in a variety of environments and make sure that they are all well adapted to survive. We want to make sure that the fields do not all die due to a drought or excess rain or some other unforeseen event. Careful precautions must be taken here in order to ensure the local system will not be affected, which is what drives up the costs for this section. Once our strands are made, tested, and viable, we can begin large-scale manufacturing of our seed starter packs. These packs can then be distributed to select communities, depending on funding. While $10 million is the predicted starting cost, distribution can be very costly based on rules and regulations on the introduction of genetically modified organisms. These permit costs could be the biggest issue, but the figures we used were for commercial organizations. Humanitarian justifications for our project, along with some political support, may be able to help reduce these costs. At this point, the project has already been implemented, so we would just conduct routine monitoring to ensure that there are no unforeseen problems. Hopefully, after 4 short years of work, we will begin to see improvements throughout areas ravaged by famine. Many populations previously occupied with finding food to survive can potentially begin to solve other problems around them. Slowly, areas we considered impoverished may be able to grow, becoming prosperous and reviving their vast cultural diversity, which they could share with the rest of the world. Grasslands can be found naturally on all continents, with the exception of Antarctica. This genetically engineered grass will increase the availability of food sources even in the harshest of climates. The grass will be very hardy and low maintenance to ensure good yield, but will be less fit compared to indigenous grasses as to have a minimal negative impact on the ecosystems. The grass will then be distributed and spread throughout the world, creating additional food supplies with very little effort. The grass will be self-sustaining and provide a food source for decades to come. The world we live in is not a forgiving one. Imagine that feeling of skipping a meal, that agonizing pain. Now imagine that feeling every waking moment of every day. Every 4 seconds, someone dies of malnourishment. That person had a family, friends, dreams. She could have been the next astronaut. He could have been an amazing artist. Hunger attacks the weakest, bringing with it pain and torment. But it's time we fight back, because until we do something, that count is only going to keep increasing.